Hello and welcome to 8.8 Improper Integrals Part 2. We continue with improper integrals of type 2. Now with type 2, a lot of times we have a point that's within the interval of integration that ends up making it an improper integral. For example, if we have between 0 to 4 and somehow we have a vertical asymptote at 2, then we have to end up splitting up the integral and doing two integrals, things like that. Okay, the idea is similar. Let's take a look at an example. It says investigate the convergence of integral from 0 to 1 of 1 over 1 minus x dx. So the one thing we notice between 0 and 1, if we plug 1 in to the function, we get 1 over 0 undefined. So it's not continuous at x equals 1, discontinuous. So what we would do then, to get a sense of it, let's draw the graph. The graph would look like this. And this would be like where the asymptote is. So this is the scenario. So here's 1. This would also be 1. And we're looking to find the area underneath this curve. So now as we do the limit, we'd have to approach 1 from the left. So it'd be 1 negative. Okay, so we would do limit as b approaches 1 from the left, integral b to 0, 1 over 1 minus x dx. So for this, easy to integrate, right? This looks like this will be an ln of 1 minus x, but we have to account for the negative. So this would be a negative ln. All right, so let's do negative ln of 1 minus x and we still got the limit. Okay, so let's plug in b, let's plug in 0, let's see what we got. We got ln of 1 minus b minus negative ln of 1 minus 0 . So we pull the negative out, we get a plus. This will be ln of 1. ln of 1 is 0. Okay, so we're left with negative ln of 1 minus b. And we got limit as b approaches 1 from the left. Okay, so now what does that give us? If b is approaching 1, that means we end up with negative ln. Now as b is getting closer and closer to 1, in here this gets closer and closer to 0. And so as ln, as you have b approaching 1 from the left, this goes to ln 0. And if we have negative ln 0, this becomes infinity. So that means that the limit is infinite and our integral would be diverging. So diverges. Okay, let's take a look at our next example. We want to evaluate this integral. Now the only problem here is when we plug 1 in, we notice we have 1 minus 1, 0 to the 2/3, which will be 0. So we have a vertical asymptote at x equals 1. Okay, so when we look at the graph of this actually, it would look like this. And we're going to 3, right? So let's say this is 3, and 0, and here's 1. So we have to split it up, 2 integrals. We'll do like 0 to 1, integral, and then plus 1 to 3. Just keep in mind for the 1, this is going to go from 1 from the left, and it's going to start off with 1 from the right. Okay, so let's do the integral from 0 to 1. So we have zero to 1 dx over x minus 1 to the 2/3. Okay, so keep in mind, very easy to integrate this. We would have, think of it like it's x minus 1 to the negative 2/3. So when we integrate it, add 1, so add 3/3 to this, we would get x minus 1 to the 1/3 divided by 1/3, which will give us, like multiplying by 3, 3x minus 1 to the 1/3. Okay, so let's introduce our limit to this. We would say limit as b approaches, we said 1 from the left, right? So 1 from the left. And then the integral would be from 0 to b dx over x minus 1 to the 2/3. And again, we integrated it. We did the work up here. So this would become 3x minus 1 to the 1/3 and we would plug in b and 0. Okay, so limit as b approaches 1 from the left of 3x minus 1 to the 1/3. So let's plug in the b. So 3b minus 1 to the 1/3 minus 3 0 minus 1 to the 1/3 Okay, so now as we take the limit as b approaches 1 from the left, as this gets closer and closer to 1, right, as this gets closer and closer to 1, minus 1, this will get 0, so let's go to 0. That goes to 0, and then we have minus 3, and then 0 minus 1 is negative 1. And this will be the cube root of negative 1, which will be negative 1 times negative 3. So we get positive 3. So this is for the integral on the left. Now let's take a look at the integral from the right. So that'll be from 1 to 3 dx over x minus 1 to the 2/3. So now when we set up the limit for here, limit as b approaches 1 from the right, maybe we should change the variable because we already used b. Let's use c. Okay, so the integral would then be from c to 3 dx x minus 1 to the 2/3. Okay, so the integral again would be, we did the work for it already, so we'd have limit c approaches 1 from the right of 3x minus 1 to the 1/3. And then we would go 3 and c. Okay, let's plug it in. So we would have 3 minus 1 to the 1/3 minus 3 c minus 1 to the 1/3. Let's do the limit. So this one gives us 3 times 2 to the 1/3 minus. So now as c approaches 1 from the right, gets closer and closer to 1, this gets closer and closer to 0, right? Because we have this getting closer to 1. 1 minus 1 would be 0. So this is going to go to 0 then. Okay, so that becomes 0. So the integral on the right becomes this. We could write this as 3 times the cube root of 2. Okay, so we had from the first integral 3, and from the second integral 3 times the cube root of 2. So final answer 3 plus 3 cube root of 2. Okay, let's take a look at another problem. Test for convergence and divergence. So sometimes we cannot evaluate the improper integral directly, when this happens, we try to figure out if the integral will converge to a number or diverge and go to infinity. If the integral diverges, that's all we do. If it converges, we use some methods to approximate the value. Okay, so the main tests for convergence or divergence for these improper integrals are the direct comparison test and the limit comparison test. Okay, so let's take a look at this first one. We'll talk about the tests as we go through it. It says, does the integral from 1 to infinity of e to the negative x squared converge? Okay, so the way we would set this up we would say limit as b approaches infinity of 1 to b of e to the negative x squared. Okay, so the one thing that's kind of preventing us from integrating it directly is the chain rule piece is not in this integrand, right? We have e to the negative x squared. We would expect maybe some kind of x. We'd probably get like negative 2x in a perfect world. We don't have either of those. Okay, so what we can do is we compare this. We compare it to a function that this function is less than. Okay. Now, when we look at the graph of e to the negative x squared, after a certain point, the graph, because we're starting at 1. So at 1, the graph of e to the negative x squared, let's do that in red, it would be a decreasing graph like this. And then that's going to be less than the graph of e to the negative x. So let's do e to the negative x in green. So this is in essence how we use the direct comparison test. We compare it to a function we compare e to the negative x squared to a function that's bigger than it. Okay, so e to the negative x is here. If you want to think area under the curve. E to the negative x squared is going to be like this. So we know that the integral, the area under the curve, 1 to b of e to the negative x squared dx, that this area will be less than or equal to the area of e to the negative x dx. And the reason why we compare it to e to the negative x, that's a larger function. No matter what happens going forward after from 1 to infinity, e to the negative x squared will not be more than e to the negative x. And e to the negative x is something that we could easily integrate. That's the other key thing here. Okay. So now we continue with e to the negative x. Okay, we integrate this. This will give us negative e to the negative x. So that gives us negative e to the negative b minus negative e to the negative 1. Limit as b approaches infinity. So now what does this become? This is e to the negative b. So this is negative 1 over e to the b. Pull out the negative, is plus 1 over e. So as b approaches infinity, if this goes to infinity, e to the infinity, 1 over that's going to be 0. And so all we're left with is 1 over e. So we know that the area under the curve of e to the negative x squared, right, that's going to be less than or equal to 1 over e. Okay. So let's get to our direct comparison test. It says that the function that we're looking at, f of x, right, first of all, both functions that we're comparing have to be continuous on the interval a to infinity. And then the function we're looking at has to be less than or equal to the comparison function, which is g of x. Okay, and so the rule is, if g of x converges, then f of x also converges. And then if f of x diverges, then g of x also diverges. Okay, so in our case, our g of x function, the one we introduced, the e to the negative x, that converged. So our function in question, the f of x, also converges. Okay, we don't know what it converges to, but all we know that in our case, our function is going to be less than, the area will be less than 1 over e. Okay, let's take a look at some other examples. Example 7. Integral from 1 to infinity of sine squared x over x squared. Okay, so let's use the direct comparison test. So now sine squared x, now keep in mind what the sine is, right? Sine is going to have a range between -1 and 1. When we square that in a sense goes between 0 and 1, right? Because all the negative ones get squared. They turn positive. So sine squared will fluctuate between 0 and 1. Okay, so a good function that we could compare it to would just be if we had, so we have sine squared x over x squared. and this will be less than or equal to 1 over x squared. Okay, and this will be obviously bigger than 0. Now 1 over x squared dx, the integral, right? So if we're comparing, this one converges. Right? Now you might say, how do we know this one converges? Well, remember we did the example of dx over x to the p. The rule was if p is greater than 1, we converge. If p is less than or equal to 1, we diverge. Right? This is what we will call eventually, we call this a p-series when we're in the chapter with sequences and series. Anytime p is greater than 1, that function or that series will converge. Okay, let's take a look at part B. Okay, so in this one, let's take a look. We have 1 over square root of x squared minus 0.01. Now, when we do the square root of an x squared, that kind of behaves like a regular x, right? If we do the square root of x squared, we get x. So now, if we take away a value from that denominator, and now we compare it to 1 over x, all of a sudden this becomes a larger fraction than 1 over x, right? Just think of it this way. If you had 1 over 2.9 versus 1 over 3, right? Which one's bigger? The 1 over 2.9. Okay, so the smaller denominator, same numerator, will always be bigger. Okay, so in this case, we have 1 over square root of x squared minus 0.1 is greater than or equal to 1 over x. And we know that integral of 1 to infinity of 1 over x dx, this diverges, right? This is a p-series where p is 1, right? So we have 1 over x to the 1. So this is divergent. So therefore the function that we're looking at in question is also divergent. Okay, so that's how this works. Okay, let's take a look at part C. Integral 0 to pi over 2, cosine x over square root of x. Okay, again, think of the cosine x. What the range is, it'll be between -1 and +1. Okay, so we have, and if we compare that to 1 over square root of x, okay, we would say that cosine of x over square root of x will be less than or equal to 1 over square root of x. At the same time, it'll be greater than or equal to 0. And so if we look at this, we could integrate this. Right, so let's integrate the 1 over square root of x. And let's pick an interval, fixed, finite interval, so that we're not going to be repeating ourselves in terms of values for the sine and the cosine. So let's do between 0 and pi over 2. Okay, so if we integrate this from 0 to pi over 2, okay, let's use the comparison one. 1 over square root of x dx. Okay, we would do a limit. Now at 0 we have an asymptote. Right, so we would do limit as x approaches 0 from the right side. Let's use a variable that we can easily identify. Let's use b. So we would go from b to pi over 2. Okay, so now we can integrate this. Keep in mind this is x to the negative 1/2. We add a power. That would make it x to the 1/2 divided by 1/2, which will mean this will become 2 times square root of x. Okay, so then if we plug this in, we get 2 square root of pi over 2 minus 2 square root of b, limit as b approaches 0. Now as b approaches 0, square root of 0 is 0, so this term on the right goes to 0. And so we're left with 2 square root pi over 2. Okay, let's write this a little neater. 2 square root pi over 2. This would mean we have, if we introduce the 2 back into the square root, that would be a 4. So we have 4 pi over 2. So we would have the square root of 2 pi. Okay, so because we have a finite number, our integral in question would converge. Okay, it's not going to cooperate, so let's say converge. Alright, let's take a look at limit comparison test. If you have positive functions, they're continuous on the interval, and if the quotient of the two functions have a limit, then we would say either both converge or both diverge. Okay, so let's take a look at this integral. We want to show that it converges by comparison with 1 over x squared dx, and find and compare the two integral values. Okay, so here we have f of x would be the 1 over x squared. So we're going to do, let's set it up, limit as x approaches infinity, we'll do f of x over g of x. Okay, so limit as x approaches infinity, and this will be 1 over x squared over 1 over 1 plus x squared. Okay, so as we simplify this, when we divide by the fraction, we multiply by its reciprocal. So this becomes limit as x approaches infinity of 1 plus x squared over x squared. So now if we take the limit as x approaches infinity of 1 plus x squared over x squared, we divide, in this case, everything by x squared. So we see that this becomes 1, 1, this is 1, this is 1, this goes to 0, so 0 plus 1, 1 over 1, okay, which is a positive finite limit. Okay, therefore we would say that the integral converges, right? So this one converges because our integral converges, right? And they would converge to different values, however, that's the only thing. So for our 1 over x squared, remember this converges to 1 over, so if it's 1 over x squared dx, this one converges to 1 over p minus 1, which in this case is 1 over 2 minus 1, which is 1. So that integral converges to 1. And then the integral from 1 to infinity of dx over 1 plus x squared, this ends up becoming an arctangent, right? So let's do that one. That would be limit as b approaches infinity, integral from 1 to b of dx over 1 plus x squared. So this gives us limit as b approaches infinity of inverse tangent of x so that means we have here inverse tangent of b minus inverse tangent of 1, limit as b approaches infinity. Okay, so inverse tangent of infinity, or as b approaches infinity, this would be 90, right? Pi over 2. So that gives us pi over 2. And an inverse tangent of 1, right? So at 45 degrees, we have a tangent of 1. So pi over 4. And so pi over 2 minus pi over 4, that would just leave us with pi over 4. Okay, so that's about it. If you have any questions, just write me an email. Have a good day. Have a good night. See you soon.